Hi, my name is Jessica and I love math. Today I will be discussing one of my favorite problems in mathematics, which involves having hyperplanes in n-dimensional space. I will attempt to describe the problem to 3 different people. The first is my cousin Clara. She is 7 years old and just started 2nd grade. The second is my friend Kenny, who is a junior at Leonia High School. The third is my father, Daniel Lee, who is a professor at Cornell Tech and manages the Samsung AI branch in New York. He has published multiple papers exploring how high-level mathematics problems can be used in machine learning. I intend to explore how having a different audience can affect the way we express our ideas to others. Okay, Clara, so I have this string right here, and I want you to cut it into 3 pieces, okay? With these scissors. Okay. So, how many cuts did you make when you made these 3 pieces?
2.
2 cuts? Right. Okay, so now I have an even bigger string, right? Yeah? And I want you to cut it into 5 pieces, okay? Okay, that's 5 pieces, right?
Yeah.
How many cuts did you make then?
4.
You made 4 cuts.
Yeah.
So, if I asked you, if you wanted to make, let's say, 100 pieces, how many cuts would you have to make?
99.
Yeah, 99. For a string, if you want to make a certain number of pieces, it could be any number. The number of cuts you have to make is 1 less than that,
Yeah.
right? Because that's how you got from 100 to 99. And so, this idea can be expanded to, like, not just a string, but, like, if you wanted to cut a cake into a certain amount of pieces, you have to make a certain number of cuts. And so, there are these things called dimensions, and so, as you go higher up in dimensions, you can still apply this argument to higher dimensions. So, Kenny, I want you to forget everything you ever knew about cutting pies.
Okay.
And cut this pie into as many pieces as you can with 3 cuts.
3 cuts.
3 straight cuts.
I mean, let's start with 1, right? Okay, 1 down. I should have made a cut a little different, whatever. That's the best I can do.
So you've made, let's see, 1, 2, 3, 4, 5, 6, 7 pieces.
7 pieces.
Which is good because that's the maximum number of pieces you can
Whoa,
make with
I'm
7.
so cool.
Yes, so I want you to cut this apple into as many.
We're going 3D?
Yes, we are going 3D. That's a good observation.
Well, I'm gonna guess it's not 7, but, you know.
Okay, good. So let's count how many pieces you made. You made 1, 2, 3, 4, 5, 6, 7, 8, which is also good because that is the maximum number of regions you
Oh,
can
I'm
make.
so cool.
Wait, hold on. We should try to put this back together so I can show you what's going on here.
Okay.
So we open up the apple to 1 cut. If you look at the cross section, this is the maximum number of regions you can make on a pie with 2 cuts. And that would be the same if you did another cut here and you opened it up again, it would look like this. So what we can do is we can make a table of what just happened. What we found here is that if you take the number of regions, which were these numbers in the table, with n dimensions and k cuts, was actually, like, if you take one number in this table, 8 here, it was the sum of the previous number, right, plus the number above that on the table. So it would be Rnk equals R of n with 1 less cut, right, plus R, and then the number above that is 1 less dimension and 1 less cut.
Mm-hmm.
Right. So that's actually it's called a recursive formula for this sequence, because you can get any number in the sequence by taking the terms that were previously in the sequence and adding them. We have this recursion, and I want to show you why it works. Remember, this was 3 dimensions and 2 dimensions. Now I want to show you 1 dimension.
1 dimension. Okay.
If you take this Twizzler and cut it with 1 cut, and say as many pieces as you can, and then and then 2 cuts. Right, and that's perfect. Okay, so now I can show you how this works. Let's say you cut this with 3 cuts.
Yeah.
Imagine you did not have this 1 cut that's right here.
Okay.
So you had this and this, right?
Okay.
So how many regions would you have?
4.
So what we're looking at is 2 numbers, and when you made 3 cuts, it was 7. So when you made 2 cuts, it was 4, and then we want to see how 3 plays into that. Okay, so imagine you didn't have, what did we say? This cut. So we had 4 regions, and then watch this. You had 2 lines, and then you cut those with a 3rd line. And so remember, when you cut a line with 2 cuts in 1 dimension, you get
3 pieces.
3 pieces. And so each of these pieces of that Twizzler correspond to 3 new regions that you made when you made the 3rd cut.
Oh, okay.
Okay, and then in the case of the apple, you had 8 pieces originally, and then when you made your new cut, creating 7 new regions, then you get 15 regions. So that's why this recursion works. This is the formula that you can use to derive any number in the sequence. Reducing the higher dimensions to lower cases is how we prove that this formula works.
Cool.
So we have this famous problem of having k hyperplane cuts in n dimensions and in general position, and counting the maximum number of regions that creates. And as you may know, that there's a recursive formula for this. The maximum number of regions you can have in n dimensions with k cuts is the sum of 1 less cut and 1 less dimension and 1 less cut. And that applies to n dimensions where n is any natural number. There's also an explicit formula, though, which is the sum as I goes to from 0 to n of the k choose I, where I can go from 0 to n. And the reason for that is, if we look in 2 dimensions, let's say we have 3 lines, so 2 flats in 3 dimensions, and we see that there are 1, 2, 3, 4, 5, 6, 7 regions. If we look at this middle region, choose a point in there, and we start slowly expanding with a circle. We want to count how many regions we pass through. We start with the one in the middle, which is k equals 3, because we have 3 cuts. So we have 3, we choose 0 for the first region. And then this 3 choose 1 comes from the individual lines. This expanding circle can only cross a new line once, so that accounts for this region, which is here, this region, which is here, and this region here. And then we see that we can enter this region through this point right here, which is the intersection of 2 lines. So that's where 3 choose 2 comes from, because that's the number of intersections between 2 lines. So this is the case for n equals 2 and k equals 3. And this expands to n dimensions, where you can have an expanding hypersphere in n dimensions. If you picture 3 dimensions, it would be a regular sphere, but then 4 dimensions it would be a half.
Very nice explanation. So one way of thinking about this is, what are the limits of this number, right? So you can prove that this number should always be less than 2 to the k. And the reason for this is For every cut, the most you can do is kind of cut up the original set of, so if in the first cut you can make your space into 2 parts. In the second cut, the most you can do is cut those 2 parts into 4 cuts, 4 regions. And then with the third cut, you can make 8 regions and so on. So this number must be less than or equal to 2 to the k.
Could you also explain it by saying each cut you can be on one side or the other side, and
Yeah.
so you think of it as a binary representation?
Yeah, so you can always be kind of adding whether you're on the left or right.
Mhm.
Now, this is very close to this number if n is very large. In high dimensional spaces, this value is almost exactly equal to 2 to k for k small. So for k much smaller than n, where n is large, this is a good approximation to this. Okay? So you can think in terms of high dimensions, what happens. And now this is significant because this is exponential in the number of cuts. Okay? So what happens is in machine learning, you think about being able to partition up a high dimensional space with a bunch of classifiers. And each classifier you can think about as a hyperplane. And so the question is, how many different regions, how many different kinds of objects can you have within this space? And this is then becomes important that it's exponential in the number of cuts, so that if you are using something like a decision tree to represent the different cuts, you can then get kind of lots and lots of regions. So this is very practical if you're thinking about machine learning and artificial intelligence, where you're trying to say how expressive is the kind of algorithm that you're trying to use. Okay? All right. Thank you very much, Jessica.